Right now, the night sky above you is filled with stars, but every single one you can see belongs to the same vast structure, a single galaxy we call home. The Milky Way is so enormous that even light, the fastest thing in the universe, takes over 100,000 years to cross it. Yet for most of human history, we had no idea just how big our home truly was. That's because measuring something this immense from the inside is incredibly difficult. Unlike distant galaxies, we can't step back and take a picture of the Milky Way from the outside. Every measurement must be made through clouds of dust and across staggering distances. This isn't a story of imagination or guesses. It's the story of how scientists measured the true size of an entire galaxy. And by the end of this video, you'll know exactly how big the galaxy you live in really is. If you're ready to go deeper into this mystery, hit that subscribe button, and together, let's drift into space. We like to think we know where we live. We say the words Milky Way as if it's a picture on a page, a spiral we can point to, a shape we can hold in our mind. But the truth is sharper. We are not standing outside our galaxy, looking in. We are buried inside it. And that creates a problem that feels almost unfair, because the one place we can never travel to is a viewpoint far enough away to see our own home whole. We can photograph other galaxies, clean, complete spirals floating in the dark. But our own is the one that refuses to sit still in a single frame. And that's where the mystery begins. Because if we cannot step outside the Milky Way, how did we ever measure it at all? Picture this. Imagine trying to measure the size of a forest while standing deep between the trees. No drone, no hilltop, no edge in sight, just trunks, branches, shadows, and layers of distance you can't read with your eyes. That is our situation, except the trees are stars and the forest is a galaxy. We live inside a rotating disk of hundreds of billions of suns, and from our position, every direction is crowded with light. Every line of sight is layered with more objects, more structure, more confusion. So when we ask a simple question, how big is the Milky Way, we're really asking something far more difficult. How do we measure a shape when we are trapped inside the shape? The night sky feels familiar. It feels close. It feels like something our minds were built to understand. But that comfort is an illusion, because our intuition was designed for distances we can walk. A street, a mountain, the far edge of the sea. Not a structure so large that light itself needs tens of thousands of years to cross it. And here's the strange part. Even when we look at the Milky Way with our naked eyes, we're not seeing the galaxy. We're seeing a thin slice, a cross-section, a bright band, because we are looking along the plane of the disk through a long corridor packed with stars. It looks like a glowing river, but rivers have banks. They have edges. The Milky Way does not offer us anything that honest, not to the eye, not to the instinct. So the first crisis is psychological. We are trying to understand something that refuses to feel real. And then comes the second crisis, a physical one. Between the stars, the Milky Way is not empty. It's filled with gas and dust, thin, cold material scattered across space. And that dust does something quietly catastrophic to our view. It blocks and scatters visible light. It turns whole regions of the galaxy into a blind spot. It's why the central regions of the Milky Way are so difficult to observe with ordinary optical telescopes, because dust in the galactic plane absorbs and scatters the light we depend on. So when we look toward the heart of our own galaxy, we are not looking into a clear distance. We are looking into fog, a cosmic fog, so deep and layered that even the brightest structures can vanish behind it. And this creates a deeper mystery. If dust can hide the center, if distance can compress depth into a flat glow, then what we think we see might be completely wrong, and scientists hate that. We can't take a clean portrait of the Milky Way the way we can with Andromeda, because to take that portrait, we'd need to be tens of thousands of light years away, above the galactic plane looking back. We don't have that vantage point, so we do what humans always do when we are denied the obvious answer. We build new senses. We replace sight with inference. We replace the photograph with a map drawn from evidence. And that's when the story cracks open, because measuring the Milky Way becomes less like taking a picture and more like solving a crime in the dark. Visible light fails us in the dusty regions, so astronomers change the rules. They learn to observe the Milky Way in wavelengths that dust can't easily stop. Infrared light, longer and less easily scattered, can pass through much of that dust, revealing stars and warm dust structures that visible light can't reach. Radio waves go farther still, slipping through dust that would completely block optical views. This is why our understanding of the Milky Way did not come from one perfect telescope photo. It came from layers of evidence stacked across the spectrum, different instruments, different wavelengths, different eyes, and every new eye solved one problem, but created another. Because once we could see deeper, we discovered the galaxy was even more complicated than we imagined. Now imagine this: simple, ordinary. You're inside your house at night and the curtains are drawn. You can see light leaking through the fabric. You can guess which rooms are bright. You can hear movement, but you cannot see the full layout from one glance. You're living inside the structure you're trying to measure. That is us. We are trying to measure a galaxy while standing behind the curtains of dust and distance. So we stop asking, what does it look like? And we start asking a more powerful question. What does it do? Here's where the Milky Way begins to confess. Even when we can't see through dust, we can still measure motion. Stars move, gas clouds drift, everything orbits. And orbit is not random. Orbit points to gravity, gravity points to mass, and mass points to structure. This is why modern Milky Way mapping is built on a quieter, more relentless approach. They measure positions, they measure distances, they measure velocities. Then they let the math of motion reveal what the eye cannot. ESA's Gaia mission is one of the defining examples of this approach, mapping our region of the galaxy in 3 dimensions by measuring the positions, distances, and motions of more than 1 billion stars. 1 billion stars, not as a poetic number, as data, as a living survey, a way to turn the sky into a measurable structure. And once we do that, something startling becomes possible. We can locate ourselves inside the Milky Way with real coordinates, not just myths, not just diagrams, real placement. The galaxy has a center. Everything says it does. The stars orbit something. The system rotates around something. But the center is buried behind dust and crowding. So how do we find it? We follow the motion. We follow the gravitational focus. We infer the point around which the galaxy turns. And the numbers become real. Our sun is about 26,000 light years from the Milky Way's center. Far enough that the galaxy is not a skyline above us, but a surrounding ocean of stars. That distance alone is already beyond anything our minds are comfortable holding. And yet, this is still only the beginning, because even if we can locate the center, we still haven't answered the true question. How big is the home that contains it? This is the brutal elegance of our situation. We can't see the Milky Way from the outside. Dust blocks the most important directions in visible light. Our instincts flatten depth into a bright band, and the galaxy has no clean edge, no obvious border we can point at and say, it ends here. So the only way forward is indirect measurement. We build distance ladders. We map star motions. We use infrared to push through dust. We use giant surveys like Gaia to triangulate where stars truly are, not just where they appear. And sometimes we use radio astronomy to trace the gas itself, because gas spreads where stars are sparse, and it can reveal structure that starlight hides. But every method depends on one thing, a single foundational concept, a quiet, almost simple idea that becomes the ruler for everything that follows. To measure our galaxy, We first have to measure distance, reliably, repeatedly at scales where intuition collapses, because the Milky Way is not measured in roads, not in miles, not in travel time. It is measured in light, in how long light takes to cross the gulf between stars. And that's where the next problem appears. Light years are not objects, they are not places. They are units of time and distance fused into one. And until we truly understand that, we cannot understand anything else we're about to measure. So here's where we stand. We are inside a galaxy we can't photograph properly, behind dust that turns whole regions into darkness, surrounded by distances that break our instincts. And yet, we still claim we know its size, but the galaxy won't give up its scale until we accept a new way of thinking, because the next step is not looking harder, it's learning what a distance really means when the ruler is light itself. And once we do that, the Milky Way stops being a picture and becomes something far more unsettling, a structure made of time, and that changes everything. A light year sounds like time, a year, a calendar, seasons, birthdays. But a light year is not time at all. It's distance, and that one misunderstanding quietly ruins everything we think we know about our place in the Milky Way. Because the moment we try to measure our galaxy, we're forced to do something that feels unnatural, almost wrong. We start measuring space with time, and once we do, the scale of our home stops being impressive. It becomes unsettling. Kilometers, miles, the numbers we grew up trusting. They were built for roads, for coastlines, for the distance between two cities on the same planet. Even the solar system begins to strain them. Earth to the moon is close enough to feel familiar, until we remember light crosses that gap in about a second. Earth to the sun is so far that even light takes about 8 minutes to arrive. That already changes the texture of reality, because it means when we look at the sun, we are watching it as it was 8 minutes ago, not now, not truly. And then we look outward, and it gets stranger. Jupiter is far enough that light can take tens of minutes. Neptune is far enough that light takes hours. We're still in our own cosmic neighborhood, and yet we're already living inside delayed information. But the Milky Way isn't a neighborhood. It's a continent of stars, and kilometers, and miles. Can't hold it. Not because they're wrong, because they're too small to be meaningful. They turn the galaxy into a number with no shape, no feeling, no gravity in the mind. So astronomy did something radical. It chose a unit that matches the only thing fast enough to cross the gulf: light. Nothing we've ever built moves like light. Not a rocket, not a probe, not a dream. NASA's fastest spacecraft are astonishing achievements, but on a galactic map, they barely move at all. At those speeds, reaching even the nearest star would take longer than the entire written history of our species, by orders of magnitude. And this is where the story fractures, because if travel can't measure the galaxy, then what can? One possibility remained: time. Not human time, not years in a diary, but the time it takes light, nature's speed limit, to cross space. That is the quiet logic behind the light year, not a poetic metaphor, a measuring stick built from the universe's fastest messenger. A light year is the distance light travels in 1 year. That's it. No mysticism, no metaphor, just a cold, precise statement of scale. And if we translate it into ordinary units, the number becomes almost useless. About 9.46 trillion kilometers. Trillion. Say it slowly, and it still refuses to become real. So we don't hold on to that number. We hold on to the meaning. A light year is the distance light can cover in a year. Moving at the fastest speed anything can move. It's not far. It's a category of far that rewrites what far even means. Imagine this. You're in your bedroom at night. You whisper a sentence. Now picture someone standing outside your house across the street. They hear you almost instantly. Now picture someone standing across your city. Your whisper is useless, so you use a phone. The message arrives so fast it feels like magic. Now take that same idea to space. In space, even light is the phone, and the Milky Way is so large that even the universe's fastest message can take years to cross what we casually call nearby. That's the scale we're entering. Not a place we can drive across, a place we can only signal across. When you look at a star, you're not seeing it as it is. You're seeing it as it was, when its light began the journey toward your eyes. For nearby stars, that delay is small. For distant stars, it becomes history, and the Milky Way is made of that delay, layer upon layer, a structure we can only understand by accepting a simple truth. We don't observe the galaxy in real time, we observe it in light time. Let's place our feet on something concrete. The nearest star system to the Sun is Proxima Centauri, about 4.24 light-years away. 4.24. That number sounds small, but it means the light leaving Proxima Centauri tonight will arrive here more than 4 years from now. If Proxima disappeared at this instant, if it simply went dark, we wouldn't know for over 4 years. And that's just the nearest neighbour, not the far edge of the galaxy, not the centre, not even close. This is the first place our mind wants to rebel, because on Earth, nearest neighbour means a short walk. In space, nearest neighbour means your entire childhood could pass, and the light still wouldn't arrive until long after you've changed. And that's where the discomfort begins, because if the nearest star is already measured in years of light travel, then a galaxy filled with hundreds of billions of stars cannot be measured like a road map. It has to be measured like a deep ocean of time. Our brains evolved for meters, for the distance to a tree line, for the walk back home before dark. We understand space by moving through it. But at galactic scale, movement becomes meaningless. Even our fastest probes, icons of human ingenuity, barely creep across the local void. This creates a bigger problem. If we can't travel to calibrate distance, how do we know what far even is? Astronomers had to build a ladder of trust, not speculation. Measurement stacked on measurement, geometry for nearby stars, standard candles for farther ones. Surveys from institutions like ESA's Gaia mission, which has mapped the positions and motions of an enormous number of stars with extraordinary precision, turning the nearby Milky Way into something almost three-dimensional. But even with our best tools, we face an uncomfortable reality. We are not measuring a single gap. We are measuring a system made of distances, a layered structure where every measurement depends on the previous one being solid. Scientists hate mysteries, and the Milky Way is one of the oldest mysteries of all, because it hides behind our own perspective. Here's the strange part. Kilometers don't fail because they're inaccurate. They fail because they don't communicate meaning. If I tell you something is 1 kilometer away, your body understands. You can picture the walk. If I tell you something is 9 trillion kilometers away, your mind goes quiet. It has no internal reference, no memory, no instinct. So astronomy does what good storytelling does. It changes the frame. It stops asking, how many steps would it take? And starts asking, how long would light take? Because time is something we can feel. A minute feels like waiting. An hour feels like distance. A year feels like change. So we use time, because time can be carried emotionally, even when distance cannot. This is the key shift. The Milky Way is not the kind of object we measure with travel. It's the kind we measure with signal delay. Light becomes our tape measure. When astronomers say a star is thousands of light years away, they're saying that star is so distant that its light has been traveling toward us since before recorded history began. When they say tens of thousands of light years, they're saying that light began its journey before the first cities rose, before the first empires collapsed. This is why the Milky Way is emotionally difficult to grasp. because it forces us to accept that distance isn't an empty gap. It's time we can never reclaim. And then the scale gets more disturbing, because the Milky Way isn't just a few light years wide. It's vast enough that light itself needs enormous spans of time to cross it. And that means when we look across our galaxy, we are not seeing one moment. We are seeing a collage of different eras, a stitched-together history arriving in photons. You're not just looking at stars. You're standing inside an archive. Every point of light is a message. Every message has a travel time, and the Milky Way is the sum of those travel times, layered into structure. This is why it's so hard to feel the galaxy, because the galaxy isn't presented to us as a single object. It's presented as delayed signals arriving from different depths, and we have to reconstruct the whole patiently, the way archaeologists rebuild a city from scattered stones. So now we understand the fundamental shift. On Earth, distance is something we conquer by movement. In the Milky Way, distance is something we measure by light. That reframes everything. The galaxy becomes a structure made of time distances, a place where how far and how long become the same question. And once we accept that, we're ready for the next trap. Because even if we learn to measure distance correctly, even if we build the ladder, confirm the numbers and trust the light, the Milky Way still plays one more illusion on us. A visual illusion, a geometric lie. Because when we look up, the galaxy doesn't look like a vast spiral system. It looks like a thin band, a flat ribbon across the sky. And that raises the next question. If our home is truly immense, why does it appear so narrow, so simple, so two-dimensional? We've learned the language of scale. We've learned that a light year is distance, that time is our measuring tool, that the Milky Way must be mapped through signals, not travel. But then the sky confronts us with a contradiction, a galaxy of staggering depth, reduced to a thin line of light. And this is where the next mystery begins, because that glowing band is not a picture of the Milky Way. It's a cross-section, a slice through a structure we are trapped inside. And once we understand why it looks flat, we begin to understand how deeply our position distorts everything we think we see. The Milky Way feels like a thing we can recognize, a pale river stretched across the night, a soft milky scar dividing the sky. But the moment we trust that picture, we fall into the illusion. Because from Earth, our galaxy looks flat, like a single glowing stripe. And the danger is simple. When something looks thin, we assume it's small. When something looks like a line, we assume we're seeing the whole. But what we're actually seeing is not the Milky Way. It's a cross-section of it. A slice. A narrow, biased view, forced on us by where we live. NASA describes it clearly. From our perspective, the Milky Way appears as a faint band of light arcing across the sky, because we're viewing the central disk edge on. That one fact should make our stomach drop, because it means the most iconic view of our home galaxy is also the most misleading. And once we realize that, a deeper mystery opens. If we're trapped inside a flattened disk, how do we ever learn what the whole structure really looks like? We grew up treating the sky like a ceiling, but the Milky Way isn't painted above us. It surrounds us. Our sun sits inside the galaxy's disk, not at the center, about 8 kiloparsecs from the core, out in a region often called the Orion Arm. So when we look toward the Milky Way band, we're not looking at the galaxy. We're looking along the plane where most of its stars are concentrated. That's why the band exists at all. It's not a boundary, it's a direction. And this creates a contradiction that the human mind hates. A galaxy is a three-dimensional structure, but our most direct view of it is a flattened line. This is where the story cracks open. Because the Milky Way is not thin like a thread. It's thin like a continent looks thin when you only see it from the side. The band looks bright, so we assume it's dense. That part is true, but we quietly make a second assumption, that the brightness tells us the galaxy is shaped like the band. It doesn't. It only tells us where our line of sight passes through the most stars. Imagine this. You're standing inside a long hallway at night. The walls and ceiling are dark, but the hallway is lined with tiny dim lights, hundreds of them, stretching far in both directions. If you look down the hallway, all those lights stack on top of each other in your view, and it becomes a bright strip. If you turn and look straight up at the ceiling, you see almost nothing. The hallway didn't change shape, only your angle did. That hallway is the galactic disk. Those lights are stars, and the bright strip is what happens when we look along the disk instead of out of it. NASA's own explanation matches this. That band is the disk of stars seen from inside the disk, telling us the galaxy is basically flat. So the Milky Way looks like a line, because we're inside a flattened system looking through its thickest direction. But then a darker detail enters. In the most dramatic stretches of the Milky Way, the bright river is torn by a black seam, a split, a crack, a long dark wound across the glow. This isn't empty space. It's dust. NASA describes these thick dust clouds blocking our view, forming what's often called the dark rift. So even the band itself, our brightest clue, arrives damaged. And that creates a bigger problem. If dust can carve darkness through the brightest part of the sky, how much of the Milky Way is hidden completely? Because dust doesn't just dim stars. It changes the story we think the sky is telling. It's the difference between looking through clean glass and looking through smoke. And once we accept that, we have to face an uncomfortable truth. Our eyes did not discover the galaxy. They only discovered a projection of it. For most of human history, the Milky Way was not understood as a galaxy. It was myth. Milk spilled across the heavens, a road for souls, a river of spirits. Then the scientific era began to tighten its grip. Galileo turned a telescope toward that pale cloud, and the cloud fractured into countless faint stars. But even that revelation didn't solve the real puzzle, because the band still looked like a band. So the next generation did what we always do when we can't step outside a system. They tried to reconstruct it from the inside. William Herschel began counting stars in different directions, star gauges, and in 1785 produced an early chart of the Milky Way's form. But later, he realized his telescope hadn't been powerful enough to reach the galaxy's edge, and he abandoned the drawing. That's the tragedy of early galactic mapping. Herschel wasn't wrong to measure. He was wrong to assume the darkness meant edge, because darkness wasn't the boundary of the galaxy, it was the boundary of visibility. And this mistake didn't just distort the map, it shaped how people imagined reality itself. For a long time, many believed the Milky Way contained everything. All stars, all nebulae, the entire cosmos. A single disk, a single island, until the universe shattered that comfort. But we don't even need to reach that later revolution yet to feel the tension, because even today, even with infrared surveys and space telescopes, the same illusion still tries to seduce us. The Milky Way looks like a thin band, so our minds want it to be simple, except it isn't. Here's the strange part. Even if the Milky Way is a flattened disk, living inside it doesn't feel like living inside something flat. Because we can't sense our position relative to the plane. We don't feel above or below the disk, the way we feel altitude on Earth. There's no galactic updraft, no slope, no horizon line. All we have are star fields and the band. So our perception is forced into a false choice. Either the Milky Way is that glowing line, or the Milky Way is unknowable. And that's when science refuses to let the emotional graph go flat. Astronomers treat the band as evidence, not as a portrait. They ask, if the band is the disk edge on, then the galaxy must extend outward, away from that strip, into regions the naked eye barely samples. But then the next problem appears. Because if the Milky Way is a disk, it must have a center, and that center should be obvious, brighter, denser, more intense. So where is it? This is the correction that changes everything. The bright band is not the Milky Way. It is the Milky Way's midplane, where our line of sight travels through the maximum concentration of stars and material. We are seeing a slice through the structure, like seeing the edge of a vast city at night and mistaking that edge for the entire city. And once we internalize that, the scale expands in our minds. We stop imagining a line. We start imagining a disk surrounding us, with thickness, with depth, with layers we can't perceive cleanly. And this is where you can feel the psychological whiplash. You've been looking at the Milky Way your whole life as a thing out there, but it isn't out there. It's the space you're already inside. The band is not a destination. It's the direction your gaze is most trapped, because that's where the galaxy is densest, and that's where dust hides the most. Which means the most famous view of the Milky Way is also the most compromised view of it. A bright ribbon, torn by shadows, masking the deeper architecture. So the illusion is complete. The galaxy looks thin. The galaxy looks simple. The galaxy looks like it can be understood at a glance, but it can't. Not from here. And now we arrive at the next fracture in the story. A disk must have a heart, a gravitational focus, a region where orbits tighten, where stars crowd and speeds rise. Yet the very direction where the galaxy should reveal itself most clearly is the direction dust tries hardest to erase. So we end with a quiet, unnerving question. If the Milky Way's shape is an illusion from our angle, and even the brightest part of it is cut by darkness, then how did astronomers locate the true center at all? They didn't do it with a photograph. They did it with something colder, something more reliable than sight. They followed motion. They followed gravity. And when they did, they found the center without ever truly seeing it. Every map has a center. A city has a downtown. A storm has an eye. A heartbeat has a chamber where the pressure begins. So we assume the Milky Way must have a center we can simply find, a bright core, a clear direction, a place we can point at and say, there. But that's not how our galaxy works. Because the Milky Way hides its center behind a wall of dust so thick that visible light collapses inside it. We can stare straight toward the heart of our home and see almost nothing. And that creates a cosmic discomfort. How do we locate the center of something we can't truly see? How do we measure a place that refuses to be photographed? This is where everything changes. Because the Milky Way didn't reveal its center through an image. It revealed it through motion, through the way stars move when they're caught in a gravitational grip they cannot escape. We're used to thinking vision is our primary sense, but in astronomy, vision is often a trap, because the universe is not obligated to be transparent. Between us and the core of the Milky Way, there's gas and dust, layer after layer, scattering, absorbing, and distorting starlight. So the galactic center is not like a lighthouse we can admire from afar. It's more like a fire behind a thick curtain. We can feel its presence, we can detect its influence, but we cannot watch it directly in ordinary light. So we do what science always does when the obvious path is blocked. We find another way in. We switch wavelengths. Infrared light can push deeper through dust than visible light. Radio waves can travel through dust with far less resistance. NASA, ESA, and ground-based observatories built entire strategies around that reality, because the Milky Way forces us to become detectives, not tourists. And the evidence we leaned on most wasn't a photograph. It was a pattern written into the sky by moving stars. When you can't see a center, you don't ask, "Where is it?" You ask something more revealing. What are things orbiting? Because orbit is confession. Everything that circles is admitting. Something heavy is here. This is the shift that reshaped our understanding. We began mapping the Milky Way not by drawing what we saw, but by tracking how objects moved. The galaxy is a rotating system. Stars and gas clouds flow around an unseen gravitational focus. Even if the center is hidden from our eyes, it cannot hide from gravity. Gravity reaches out, silently, and forces order onto chaos. And once we started measuring that order, velocities, directions, orbital shapes, the Milky Way's secret began to unravel. Picture a playground carousel. Now imagine the middle is covered by a thick blanket, so we can't see what's at the center, but we can still watch the children holding on. If they're circling fast, pulled inward, struggling to keep their grip, we don't need to see the center to know something powerful is anchoring the motion. That's what the galactic center is like. We can't lift the blanket, so we watch the orbit, and the orbit tells the truth. For decades, astronomers focused on the sky region towards Sagittarius, where the dense star fields and radio emission hinted at something deeper. But hints aren't enough. Scientists hate mysteries that can't be tested, so they did something painstaking and almost unnatural for the human mind. They watched individual stars near the hidden center for years. Not minutes, not nights, years. Using infrared telescopes with extreme resolution, facilities like the Keck Observatory in Hawaii and the European Southern Observatory's Very Large Telescope in Chile, teams tracked stars moving in tight loops around a dark point. Those stars had names like S2, not poetic, not romantic, because the data mattered more than the name, and what the data showed was unsettling. Some of these stars were orbiting so quickly, completing a full loop in about 16 years, that there was only one explanation consistent with physics. They were circling an object with enormous mass, packed into a very small region. A gravitational focus so intense it could only be, by modern consensus, a supermassive black hole known as Sagittarius A star. This wasn't guessed from a single observation. It was built from relentless tracking, careful measurement, and independent confirmation, work strongly associated with astronomers like Andrea Ghez and Reinhard Genzel, and later refined with even sharper instruments. We didn't see Sagittarius A star the way we see a star. We saw what it did to everything around it, and that is often the purest form of evidence. The center of the Milky Way is not calm, it's crowded, packed with stars so densely that the sky there isn't black. It's thick with light, but it's also violent in ways we can detect. There are powerful magnetic fields, shocks and gas, remnants of supernova explosions. Radio and infrared surveys reveal streams of gas moving, heating, collapsing, forming stars, being torn apart, an ecosystem driven by gravity and energy. It's a region where the normal, quiet night sky feeling dies, because the center isn't a peaceful destination, it's the engine room, and it's hidden from our natural senses, so everything we know about it comes through instruments and inference. This creates a deeper mystery. If the center is so energetic, why does it look so silent from our backyard on Earth? Because distance isn't just space, distance is delay. And at these scales, the galaxy teaches us humility. The center can be roaring, and we still receive it as a whisper. There's a measurement that sits at the foundation of this entire story. The distance from Earth to the Milky Way center is about 26,000 light years. That number is not just a statistic, it is a psychological fault line. Because 26,000 light years means the light reaching us from near the center began its journey when human civilization was still in its early chapters, long before modern cities, long before our technology, long before most recorded history. We are not looking at the center as it is now. We are looking at it as it was, tens of thousands of years ago. And yet, even with that delay, we can locate it. We can place it on our maps. We can measure its distance. Not perfectly, not without uncertainty, but with enough confidence to build the next steps of the galactic blueprint. That's the triumph. But it comes with a cold implication. We didn't find the center because it welcomed our eyes. We found it because we learned to read the handwriting of gravity. Imagine this. You're in a huge stadium at night and the lights are off. You can't see the center field, but you can hear it. You can hear where the crowd is loudest. You can sense where the vibration is strongest. So you don't walk blindly. You listen. You track the echoes. You follow the motion of sound. That's what we've done with the Milky Way. We're sitting in the stands far from the field, and we still found the middle, not by sight, by influence. So now we can say something precise, and it matters. The center of the Milky Way is a real location in space, buried behind dust, marked not by a visible beacon, but by the orbits of stars and the flow of gas. We locate it because stars near the core move as if they're bound to a compact, massive source. Infrared observations allow us to track those stars through the dust. Radio observations reveal structures and motion in gas that outline the central region. Multiple major observatories and research teams have converged on the same conclusion. This is scientific restraint, not one method, not one telescope, a converging web of evidence. And when all of that evidence meets, a dark object sits at the center of our galaxy, shaping the motion of everything around it. We don't have to romanticize it. It's already cinematic. A hidden heart that cannot be photographed in ordinary light, yet announces itself through the choreography of stars. But this relief doesn't last, because now that we've pinned down the center, we face a larger question that threatens to swallow everything we've built so far. We've found the heart of the Milky Way without seeing it. We've located the gravitational focus. We know it's roughly 26,000 light-years from us. But then the next question arrives. Quiet, heavy, unavoidable. If we can find the center, how far does the galaxy extend in every direction from that center? Where does it truly end? Because the Milky Way doesn't have clean borders. Its edges are faint. Its outer regions blur into darkness, and when we try to measure its width, its true diameter, the galaxy pulls the same trick again. It refuses to draw a line, and that's where we go next. If we could step outside the Milky Way for just a moment, the question would be easy. We would look back. We would trace the spiral. We would draw a circle around the edge and say, this is the width. But we can't. We are trapped inside the disk, inside the light, inside the dust, inside the noise. So when we ask how wide our galaxy is, we're asking something more unsettling than it sounds. Where does home stop when there's no wall to touch? Because the Milky Way doesn't end like a city ends. It thins, it fades, it dissolves into the dark. And that means the edge isn't a line. It's an argument, a careful, scientific argument built from star maps, radio whispers, and the rotation of the entire galaxy. And the moment we think we've pinned it down, the galaxy does what it always does. It makes the answer feel incomplete. When we say the Milky Way's width, we're really talking about diameter, the distance from one side of the main disk to the other, passing through the center. But even that definition hides a trap, because galaxies have layers. There's the bright, visible disk, the part most people imagine. There's gas farther out that doesn't shine like stars do. There are faint, stellar structures that extend beyond what the eye would ever notice. So the Milky Way's width depends on what we choose to measure, the visible, starry disk. The gas disk, traced by radio emission, the extended structures that are real, but faint, almost ghost-like. This is why astronomers don't give a single perfect number carved in stone. They give a range, and the most commonly cited range for the Milky Way's diameter is about 100,000 to 120,000 light-years. That is not a guess. It's the best convergence of multiple methods, Different instruments, different wavelengths, different assumptions, arriving at the same haunting scale. But this is where the story cracks open. How do we measure a width that fades instead of ending? In everyday life, edges are simple. A room ends at a wall, a street ends at a curb, a coastline ends where water begins. But a galaxy isn't built like that. A galaxy is built like smoke. The farther you go, the thinner it becomes. Stars don't stop suddenly. They become rarer, dimmer, harder to detect. Gas clouds drift farther out than the bright star fields. Some structures warp, bend and flare. And dust complicates everything, again, by hiding parts of the disk, especially when we try to see through the thickest regions. So when astronomers talk about the edge of the Milky Way, they're not pointing to a border, they're defining a threshold, a point where the disk becomes so sparse, so faint, that the galaxy stops behaving like a dense stellar city and starts behaving like deep space. But then comes the brutal question: how do we locate that threshold from inside the galaxy itself? We can't draw it by sight, so we do it by mapping what we can detect. And this is where the methods begin. At the most basic level, astronomers do something ancient. They count, not casually, but systematically, across the sky, across directions, across distances. Modern surveys, using ground-based observatories and space missions like the European Space Agency's Gaia, measure positions, distances and motions for enormous numbers of stars. This isn't stargazing, it's cartography. It's building a three-dimensional map from inside the structure. And with that map, we start to see patterns, where stars are dense, where they thin out, where the disk's population begins to fade. But star mapping has a problem the galaxy uses like armor. Stars get harder to see at distance, especially through dust. So star counts alone don't give us the whole diameter. They give us a strong foundation, but not a final border. And that creates a bigger problem. If stars don't reveal the full width, what does? This is where the Milky Way becomes even stranger, because the galaxy is not just stars, it's also gas. Vast amounts of hydrogen spread through the disk, cold, thin, and mostly invisible to our eyes. But hydrogen has a signature astronomers can detect in radio waves, the famous 21 centimeter emission of neutral hydrogen. It's quiet, it's precise, and most importantly, radio waves can travel through dust far more easily than visible light. So even when the galaxy hides behind darkness, hydrogen still speaks. Radio observatories, built by institutions and nations, often collaborating across continents, can map hydrogen across the Milky Way in sweeping surveys. And when we trace that hydrogen, we discover something unsettling. The gas disk often extends beyond the bright stellar disk, meaning the visible Milky Way is not the full Milky Way. What our eyes call the galaxy is only the part that shines strongly. But the structure continues, thinner, wider, fainter, and that's when the edges start to feel less like a conclusion and more like a fade out. Picture this. You're in a huge field at night with a flashlight. Near you, the grass is bright and obvious. A few steps farther, it's dimmer. Farther still, you can't see the grass at all. Now ask, where does the field end? The field didn't end. Your light did. That's what happens in a galaxy. Our edge is often defined by what we can detect, not because the galaxy stops existing beyond that, but because it becomes too sparse, too faint, too spread out to show itself easily. Astronomers know this. That's why they don't pretend the Milky Way has a crisp outline. They measure it the way you measure a fog bank, by how quickly it thins, not by where it cuts. But then, there's a deeper tool, one that doesn't rely on brightness, one that listens to the galaxy's motion itself. Here's the disturbing beauty of it. Even if we can't see everything, everything still moves. Stars orbit the galactic center. Gas clouds orbit the galactic center, and those orbits can be measured. Astronomers use Doppler shifts, changes in light or radio frequencies caused by motion, to measure how fast gas and stars are moving at different distances from the center. This produces what's called a rotation curve, a profile of orbital speeds versus distance, and this matters for our question of width, because rotation curves help reveal how far the disk's rotating material extends, where organized disk-like motion becomes sparse or harder to trace, how mass distribution shapes motion even where light is faint. This method doesn't see the edge in the way our eyes want. It infers the structure from dynamics. This approach became historically powerful in the 20th century, with astronomers like Vera Rubin helping demonstrate that galaxy rotation doesn't behave the way simple visible matter expectations would suggest, an observation that later became central to the dark matter story. We won't open that door fully yet, but it's standing there, because when we ask how wide the Milky Way is, we're inevitably brushing against the fact that much of its structure is revealed by gravity, not light, and that makes the measurement both stronger and more unsettling. When astronomers combine these methods, star mapping, especially in wavelengths and surveys that reduce dust bias, hydrogen mapping in radio rotation and dynamics as an independent check, they converge on the same broad truth. The Milky Way's main disk spans roughly 100,000 to 120,000 light-years across. That number is not just large, it's psychologically violent. It means light, moving at the fastest speed in the universe, needs 100,000 years just to cross our home from one side to the other. Not travel time, light time, which means the Milky Way is not just big, it is so big that even information struggles to cross it. So when we look across the disk, we are never seeing a single moment. We are seeing a time-smeared structure, layers of past stacked on top of each other, and that changes the emotional meaning of home. Home is not a place we can fully witness at once. Home is a structure too vast for a single perspective. Now we have to separate two ideas that people often merge: the bright disk, the part that looks like the Milky Way band, and the extended galaxy, the larger, fainter, more complex reality. The bright disk is where star density is high, where the glow is thick enough to paint the sky. But beyond that region, the galaxy continues. Gas extends farther out than the bright star fields. Stellar populations thin, but don't vanish instantly. The structure warps and bends like a vinyl record left too close to heat. Still a disk, but no longer perfectly flat. So when someone asks, "How wide is the Milky Way?" we have to ask back, do you mean the part we can see easily? Or the part that still belongs to the disk, still rotates with the galaxy, still carries mass and structure, just without the bright glow? Astronomy answers by giving us ranges and definitions, not a single dramatic line. Because galaxies are not drawn with ink, they're drawn with probability, density, motion. Imagine you're standing in a city at night. You can see the bright downtown, towers, signs, traffic. It feels like the city, but you know the city doesn't end where the bright lights end. It continues into darker neighborhoods, quieter streets, places with fewer lights but still full of people and homes. That's the Milky Way. Our eyes catch the downtown glow of the disk, but the galaxy's true span includes regions that are real, measurable, yet too faint to feel emotionally obvious. And that's why width becomes a careful statement, not a simple one. So here's what we can say with confidence. The Milky Way's disk is vast, on the order of 100,000 to 120,000 light-years across. We measure it through multiple lines of evidence: star surveys, gas mapping, and galactic rotation. The edge is not sharp because the disk thins gradually, and different components extend to different distances. The visible Milky Way is only the most luminous part of a larger structure, And this matters for more than trivia, because once we know the width, our position becomes real. We are not just somewhere in the galaxy. We are inhabitants of a disk so wide that light needs 100 millennia to cross it. Our entire species, every language, every war, every love story, exists as a flicker inside this enormous rotating architecture. And yet, the width is only one dimension, a single measurement, a comforting line drawn across a thing that is not truly a line. Because the galaxy has another dimension that people forget, one that changes the feeling of the Milky Way completely. Now we've measured the width, we've carved a diameter into the darkness, but the Milky Way is not a flat diagram, it's not a coin, it's not a ribbon pasted onto the sky. It has thickness, it has layers stacked above and below the disk, regions where stars are rarer but still real. And when we finally ask how thick the Milky Way is, we discover something that disturbs the simple mental image forever. Because flat does not mean small, and the forgotten dimension is waiting. We've finally given the Milky Way a width, a span so vast that light needs 100,000 years, sometimes more, just to cross it, and our minds do what they always do. They flatten it, they turn it into a diagram, a bright spiral on a black background, a thin, elegant disk. It feels understandable, it feels safe. But that comfort is another illusion, because the Milky Way is not a flat picture, it has thickness. And once we ask about that thickness, once we ask how tall our galaxy really is, the Milky Way stops feeling like a ribbon and starts feeling like a structure we are truly buried inside. And this creates a bigger problem. If the galaxy is thin, why does it still contain hundreds of billions of stars? Where do they all fit? And what does thin even mean? When the scale is cosmic. When astronomers call the Milky Way thin, they are not saying it's small, they're speaking in ratios. Compared to its enormous width, the disk is relatively slender, more like a wide, stretched plane than a sphere. But even that slender plane is gigantic. The Milky Way's stellar disk has a thickness on the order of about 1,000 light-years for the thin disk, with a thicker component extending to several thousand light-years. Those numbers are not decorative. 1,000 light-years means light itself needs 1,000 years, just to cross the disk's vertical depth in the densest region. So yes, it's thin compared to a width of roughly 100,000 light-years. But thin is not fragile, thin is not minor. In a galaxy, thin can still mean a dimension that swallows entire human histories like dust. And the moment we accept that, the question changes. We stop asking how wide the Milky Way is. We start asking what kind of structure it truly is. From Earth, the Milky Way looks like a bright band. That view encourages one mistake. We assume the galaxy is basically a flat sheet of stars, but that band is our side-on view through the disk. We're looking across a layer, and when you look across a layer, you don't naturally sense its height. You sense its density. So the Milky Way's thickness is not obvious to the eye, not even close. Dust also plays its role again, dark lanes cutting across the band, hiding entire populations of stars and making the disk seem cleaner and thinner than it really is. So astronomers had to measure thickness indirectly, not by how the Milky Way looks, but by how stars are distributed above and below the galactic plane. And this measurement revealed something quietly profound. The Milky Way is layered, not a single sheet, a structure with multiple components stacked like different atmospheres. Astronomers describe at least two main disk components: the thin disk. This is where much of the Milky Way's gas and dust lies. It's where star formation is active. It's where many of the younger stars live, including our Sun. It's relatively compact vertically, on the order of about 1,000 light-years thick. This is the disk our night sky band mostly represents. But it's not the whole story. The thick disk above and below the thin disk is a thicker population of older stars, less gas, less dust, less star formation, but a broader vertical spread, extending to several thousand light years. This thick disk is quieter, older, more diffuse, and it proves something important. The Milky Way is not a clean, single-layer object. It's a history written in vertical structure. Older stars have been stirred and scattered over time by gravitational interactions, mergers, passing satellite galaxies, and the long dynamical evolution of the disk. And that's where it gets stranger, because once we accept the disk has thickness, we have to confront something even more visually misleading. The Milky Way isn't just a disk. At the center, the disk swells. It becomes the bulge, a dense, crowded, star-packed region that rises above and below the plane, far more than the disk does. This bulge is not a small bump. It's a colossal structure composed largely of older stars, packed into a region near the galaxy's core, and it changes the silhouette of the Milky Way completely. If we could see our galaxy from the outside, it wouldn't look like a perfectly flat vinyl record. It would look like a disk with a thickened center, like a coin with a raised hub. But we can't see it from outside, so we infer it from star counts, infrared mapping through dust, and the motions near the center. This is where NASA and ESA infrared surveys become essential. Visible light fails, but infrared reveals crowded star fields deeper into the central region, and the bulge matters for scale because it answers a question our intuition keeps asking. If the Milky Way is thin, where is the weight? Where is the density? The bulge is one major part of that answer. But there's another. Here's the uncomfortable truth. The Milky Way's stars are not evenly spread like sugar sprinkled on a table. They cluster. They concentrate. The disk contains a massive number of stars, but star density rises dramatically toward the center. The bulge, the inner regions of the disk, the central bar-like structure astronomers infer from star distributions. These are places where the galaxy's stellar population thickens. So when we picture the Milky Way, we often imagine a tidy spiral with arms made of stars, evenly spaced. But real galaxies aren't tidy. They're shaped by gravity over billions of years. They contain regions of compression and sparsity, neighborhoods where stars are common, and outskirts where stars are rare. That's why thickness matters, because thickness tells us where gravity has sculpted the structure, where stars are piled up, where time has stirred populations, where the galaxy's internal architecture becomes three-dimensional. And this leads to a bigger misconception we need to shatter. Flat is not the opposite of massive. Imagine this, a pizza laid on a table. It's wide, almost the width of the table itself. But the crust is thin, only a small rise above the surface. From the side, it looks like almost nothing. Now translate that. If the Milky Way's width is the pizza, its thin disk height is the crust. Thin doesn't mean tiny. It means most of the galaxy's material is compressed into a narrow plane, a layer where stars form, where gas gathers, where dust thickens, where spiral arms live. A vast, flattened habitat. Not small, just concentrated. So how do they measure this vertical depth? They do it by mapping stars in 3 dimensions. They measure distances. They measure positions. They measure how star density changes as we move away from the galactic plane. ESA's Gaia mission provides crucial data for nearby stars, distances, positions, motions, allowing astronomers to model the disk's structure around us with unprecedented detail. For regions further away, especially toward the dusty center, infrared surveys step in, because in visible light, the plane becomes a wall, and then dynamics helps again. Stars above and below the plane move differently. Their motions reflect the gravitational potential of the disk and bulge. So thickness is not a guess, it's an observed pattern, a measured distribution, a real dimension of our home. But there's a psychological consequence here that most people never consider. Thickness changes what inside the Milky Way truly means. Imagine you're inside a massive layered cake, not a slice, the whole cake. You can walk sideways for days and still be inside it, but you can also go up and down through layer after layer, each one different in texture and density. That's what inside the Milky Way means. We're not inside a flat drawing. We're inside a three-dimensional structure with layers, thin disk, thick disk, bulge, each with different stellar ages, different densities, different histories. And once we grasp that, the Milky Way stops feeling like a ribbon in the sky. It starts feeling like a volume, a habitat, a gravitational ecosystem. So here's what this dimension gives us. The Milky Way is thin only in comparison to its width. The disk still spans roughly 1,000 light years in its thinner stellar layer, with thicker components extending several thousand light years above and below. The central bulge rises far above the plane, adding massive vertical structure near the core. Thickness reveals history. Older star populations are distributed differently than younger ones. This is why it matters. Because a flat mental image makes us underestimate the Milky Way's scale. We imagine a surface, but we live in depth. We live in layers. We live inside a system that is not merely wide, but volumetric. And yet, even this isn't the end of the story, because once we step into the third dimension, we run into something darker, something that makes the Milky Way's true size explode outward beyond everything we've measured so far. We've measured width, we've confronted thickness, we've upgraded our mental picture from a ribbon to a structure. But then the universe delivers its next twist. Most of the Milky Way's mass is not in the stars we see, not in the gas clouds we map. There is an invisible component shaping the galaxy's gravity, stretching far beyond the visible disk. A halo of matter we cannot see directly, but whose presence is written into motion. And once we enter that territory, the Milky Way becomes larger than its light, larger than its stars, because the next dimension of scale isn't just vertical, it's invisible. We've been measuring the Milky Way by what we can see, by the bright band, by star counts, by gas traced in radio, by a disk with a width that stretches for about 100,000 to 120,000 light years. It feels like a conclusion. But then the universe delivers its most unsettling twist. Most of the Milky Way is not visible, not dim, not hidden behind dust, invisible. And what makes this truly disturbing is, the invisible part is not a small detail, it is the majority. The Milky Way we see, the stars, the glowing gas, the central bulge, may be only the luminous skin of something far larger, a structure that extends far beyond the last bright stars, a halo that reaches outward into darkness, still holding our galaxy together. And once we accept that, the question changes. We stop asking, how big is the Milky Way? We start asking, how big is the Milky Way's gravity? Because gravity doesn't end where light ends. Astronomers didn't invent dark matter because it sounded dramatic. They were forced into it. Because when they measured how galaxies rotate, the numbers refused to behave. In the mid-20th century, astronomers like Vera Rubin helped show something that should have been simple. Farther from a galaxy's center, stars should orbit more slowly, because most visible mass is concentrated toward the middle. But galaxies didn't do that. Their outer regions kept moving fast, as if there was extra mass we couldn't see, extending far beyond the bright disk. This wasn't just one galaxy, it was many, and it created a cosmic discomfort. Either our understanding of gravity was wrong, or most of the mass in galaxies was missing from our view. Scientists hate mysteries like that, so they followed the evidence, and the evidence kept pointing to the same conclusion. There is more to the Milky Way than its light. The Milky Way is a rotating system, Stars orbit the center. Gas clouds orbit the center. And orbits are brutally honest, because orbital speed is controlled by mass, not by beauty, not by brightness, by mass. So astronomers map the Milky Way's rotation using multiple tools. Radio observations of hydrogen gas, which can be measured through dust. Stellar motions in surveys like ESA's Gaia, which measures positions and speeds with extraordinary precision. The motions of objects far from the center, globular clusters, satellite galaxies, whose paths are controlled by the Milky Way's full gravitational field. And again, the same pattern appears. The galaxy's visible matter can't fully explain the speeds we observe. The outer regions behave like they are held by a much larger unseen structure, and that creates a bigger problem. If the Milky Way's gravity reaches farther than its stars, how far does it reach? Imagine this. You walk into a massive warehouse at night with a weak flashlight. The beam lights up a small circle on the floor. You might think the warehouse is only as big as the lighted patch, because that's all you can see. But the walls don't stop existing when the light stops reaching them. The warehouse is still there, silent, enormous, beyond the beam. That is what the Milky Way is doing to us. Starlight shows us the bright interior, but gravity reveals the walls. And the walls of the Milky Way are not made of stars. They are made of mass we cannot see directly. Astronomers describe the Milky Way's invisible component as a dark matter halo. Not a ring, not a flat plane. A halo, roughly spherical, extending far above and below the disk and far beyond the visible edge. It's not a cloud we can photograph. It's a gravitational presence inferred from how everything moves. This halo is thought to contain most of the Milky Way's mass. The exact numbers vary by method, but the broad conclusion is stable across modern research. The Milky Way's total mass is often estimated around about 1 trillion times the mass of the Sun, give or take, and the visible matter, stars, gas, dust, is only a fraction of that, meaning the galaxy we live in is embedded inside a much larger gravitational body. We're not just inside a disk, we're inside a halo, and once we see that, the Milky Way becomes larger than our mental picture can comfortably hold. Here's the strange part. Stars behave like they're orbiting an invisible architecture. They don't know what dark matter is. They don't care about our theories. They move according to gravity, and gravity is telling us something enormous is there. We see this in multiple ways. 1. The speed of rotation. The outer parts of the Milky Way rotate faster than visible matter alone would predict. That mismatch is one of the classic fingerprints of dark matter. 2. The motions of satellites. The Milky Way has companion galaxies, smaller satellites that orbit it over billions of years. Their speeds and trajectories are controlled by the Milky Way's total mass, not just its bright disk. When astronomers model these orbits, they consistently find that the mass extends far beyond the visible stars. 3. Stellar streams, the galaxy's torn threads. When small galaxies or clusters are pulled apart by the Milky Way, they leave behind long stellar streams, thin stretch trails of stars. These streams act like test particles. Their shapes and motions trace the Milky Way's gravitational field, and what they trace is not a neat disk-shaped gravity source. They trace a larger halo-dominated potential. It's eerie because it means the Milky Way is wrapped in something that reveals itself only through motion, and that leads to a disturbing realization. To understand our galaxy's true scale, we have to accept a kind of blindness. We are measuring a structure we cannot directly see. We can't see wind, but we see what it does. A tree bending, dust lifting from the road, ripples travelling across a pond. Dark matter is like that in our measurements. We don't see it. With a telescope like a glowing star. But we see it in the bending of orbits, in the way stars and gas refuse to fly apart, in the way the Milky Way holds together as a coherent rotating system. The halo is not visible light. It's a gravitational weather system surrounding our galaxy. This is where the Milky Way becomes psychologically heavier, because our instincts want to believe that the brightest things are the most important things. But in galaxies, brightness is not dominance, mass is dominance, and the visible Milky Way, the part that paints the sky, appears to be only a minority of the galaxy's total mass. That's not poetic. That's what the evidence implies across decades of observations. So when we talk about the Milky Way, we're really talking about two overlapping realities. The Milky Way of light, the disk, the bulge, the stars we can count. The Milky Way of gravity, a halo extending far beyond the light, shaping everything, and this makes our earlier measurements feel incomplete, because a diameter of 100,000 to 120,000 light-years describes the main luminous disk. But the galaxy's gravitational influence extends much farther. Far enough that the Milky Way doesn't feel like a single object anymore. It feels like a domain, a region of space where the Milky Way is the dominant gravitational presence. And that's the scale that truly matters. Because gravity defines what belongs to the galaxy. Even if the outer halo is faint to the eye, it still matters, because it controls how our galaxy captures and holds satellite galaxies, how gas flows in and out over cosmic time, how the Milky Way interacts gravitationally with its neighbours, including Andromeda. This is not a decorative add-on. This is the underlying framework. It's the reason the Milky Way can be wide and thin and still remain bound. It's the reason stars at the outskirts don't simply drift away into intergalactic night. So when we ask, how big is the Milky Way? We should be honest. The Milky Way is not just the part that shines, it's the part that holds. And what it holds extends far beyond the bright disk. Picture yourself standing under a dark sky far from city lights. You can see the Milky Way as a band, bright, obvious, undeniable. Now imagine walking outward from that band, not with your feet, but with your mind, past the last bright stars, past the thin outskirts where the disk fades, into a region where the sky looks empty. It wouldn't feel like the galaxy anymore, but gravity would still be there, still shaping motion, still pulling, meaning the Milky Way would still be present, even when it no longer announces itself with light. That's the quiet terror of it. The galaxy does not end where our senses end. So here's what this chapter gives us clearly. The Milky Way's luminous disk is vast, but it is not the whole galaxy. Multiple lines of evidence show that galaxies, including ours, contain far more mass than what we can see in stars and gas. That extra mass is described as a dark matter halo, an extended structure that dominates the galaxy's gravitational influence. The Milky Way's true scale is not just about how far its light reaches, but how far its gravity reaches, and that reshapes the emotional meaning of home. We are not living inside a simple disk of stars. We are living inside a gravitational empire, a structure whose majority is invisible, yet measurable, a presence we can't photograph but can map through motion. But this answer doesn't close the story. It opens a deeper one, because once gravity becomes our ruler, time becomes unavoidable. We've been measuring space, width, thickness, visible edges, invisible halos. But the Milky Way's deepest truths keep arriving the same way, through movement, through orbits, through the slow clockwork of stars traveling around a hidden center, inside a halo we cannot see. And that raises the next question. If motion is our most reliable measuring tool, what does the Milky Way look like when we measure it in time? Because our sun is not standing still inside this galaxy. It's racing, quietly, relentlessly, around the center. And one full lap takes longer than human civilization has existed. That is the next scale we have to confront. Not distance, time. We think a year is a familiar thing, a loop of seasons, a birthday candle, a calendar turning like a quiet wheel. But inside the Milky Way, year becomes something else entirely, because our galaxy has its own clock, a clock measured not in days, but in orbits. And once we listen to that clock, something unsettling happens. The Milky Way stops feeling like a place we live. It starts feeling like a machine we're riding, a vast rotating system that turns so slowly, so relentlessly, that human history becomes a blink inside a single revolution. This should be comforting. Motion means structure. Structure means we can measure, except the scale of that motion shatters our intuition, because even at unimaginable speed, the galaxy still doesn't feel smaller. It feels larger. And this is where everything changes, because time, quiet, cold, patient time, becomes one of our most powerful measuring tools. Out in the Milky Way, distance is already strange. Light years turn space into delay, but motion turns space into time. We're not standing still inside our galaxy. Our sun is orbiting the Milky Way's center, sweeping through the disk as the galaxy rotates. Astronomers call the time for one full orbit a galactic year, and that number is almost impossible to hold. A single galactic year is about 225 to 250 million Earth years. One lap around the galaxy's center takes longer than the time since dinosaurs first appeared and vanished. That is the scale we're dealing with. And it immediately raises a question that feels like a trap. If our galaxy's year is that long, how many times has the sun completed this journey? The answer is both simple and unsettling. Our solar system is about 4.6 billion years old. That's not a philosophical number. That's a measured age, built from radiometric dating, meteorites, and the consensus framework modern planetary science relies on. So if one galactic year is roughly 225 to 250 million years, then the Sun has completed only about 20 to 25 orbits around the Milky Way since it formed. That's it. All of Earth's oceans, all of life's evolution, every empire, every language, every war and library and song happened inside a small number of galactic years. We are not ancient in the galaxy. We are recent. We are a brief weather pattern inside a turning storm. But then the universe delivers another twist. Even though the Sun has completed only a few dozen orbits, it has been moving at extraordinary speed the entire time. And speed, at human scale, usually shrinks distances. Except here, speed does the opposite. Our Sun travels around the galactic center at roughly about 220 kilometers per second, or roughly 829,000 kilometers per hour. A commonly cited value based on measurements of the Sun's motion relative to the Milky Way's rotation. That's fast. Fast enough to cross continents in minutes, if space had roads, but space doesn't. And when we translate that speed into meaning, we collide with something cold. Even at hundreds of kilometers every second, it still takes hundreds of millions of years to complete one orbit. So speed doesn't make the galaxy feel smaller. Speed makes the galaxy feel more immense, because it reveals how deep the track truly is. We are racing, quietly, invisibly, through the Milky Way right now, and yet we barely move in any way that our senses can detect. We wake up, we go to work, we live our lives, while the solar system is sweeping around the galaxy like a leaf caught in a river current. This is the strange part. Our daily stillness is happening inside cosmic motion, and once we accept that, motion becomes more than movement. It becomes a ruler. Astronomers don't measure the Milky Way's scale only by looking outward. They measure it by watching how stars and gas move. Because in a galaxy, motion carries information. Orbital speeds reveal mass distribution. Patterns of rotation reveal structure. The way stars stream and drift reveals past collisions and gravitational shaping. This is why missions and surveys matter so deeply. ESA's Gaia mission, for example, measures positions and motions for vast numbers of stars, turning the Milky Way into a living dataset, a map made not of ink, but of trajectories. And across NASA missions, ground-based observatories, and decades of astrophysical research, the same principle repeats. When the galaxy won't show its full shape in a single image, it reveals itself through choreography, through the way its contents move under gravity. Einstein's work made this kind of thinking unavoidable. Space and time are not separate in the deep structure of reality. In the Milky Way, we don't just talk about that idea, we live inside it, because the galaxy is a physical system whose scale is written into its time. But that creates a new problem. If our sun is orbiting, where exactly has it been? We often imagine the solar system as a stable home, a safe neighborhood in a calm galaxy. But the Milky Way is not calm. It has spiral arms where star formation is active, regions filled with gas, dust, and the violent births of massive stars. Massive stars don't live long. They explode, and supernovae don't care about stories. They reshape space with shockwaves and radiation. So the sun's journey around the Milky Way is not just a slow loop. It is a path through regions of different density, different danger, different history. Over hundreds of millions of years, the solar system drifts relative to spiral patterns, moving through zones where the night sky would have looked unfamiliar, thicker with star fields, richer with nebulae, sometimes more turbulent. We don't always feel that motion, but the galaxy remembers it, and astronomers look for those memories in the motion of stars, stellar streams, moving groups, and the signatures of past interactions, because motion is history, and history is scale. Imagine this. You're inside a gigantic stadium in the dark. You can't see the walls, but you can see a single glowing runner on the field, running in a circle. If the runner completes one lap in 10 seconds, the stadium might be small. If the runner completes one lap in 10 hours, the stadium must be enormous. You don't need to see the walls. The time of the lap tells you the size of the arena. That's what a galactic year does. It's a lap time that reveals the scale of the structure we're inside, and our lap time is hundreds of millions of years. So even before we draw a spiral, even before we argue about the exact edge, the galaxy's own motion tells us we're in something vast beyond the reach of intuition. But there's another layer, because when we use time to measure the galaxy, we bump into a strange truth. We never observe the Milky Way in a single moment. Every star we see is delayed light, information arriving late, and when we talk about the sun completing 20 to 25 orbits, we're describing a journey we know through physics, not through direct witnessing. No human has watched a galactic year pass. No civilization has recorded the full loop. We infer it. We calculate it from our position, our velocity, our measurements of the galaxy's rotation. This is not weakness. It's strength. It means our understanding is not based on one lifetime. It's based on laws of motion that hold across lifetimes. Stephen Hawking often spoke about the power of physics to reach beyond the scale of human senses, how mathematics and observation together allow us to speak about times we cannot personally endure. This is one of those moments. We cannot live long enough to feel a galactic year, but we can still measure it. We can still know where we are in the turning, and that knowledge changes our relationship to home. You can feel your own life in years, in school terms, in memories, in family generations. Now imagine trying to place that against a clock where 1 year is 225 to 250 million Earth years. Your lifetime doesn't even register, not because it's meaningless, but because the Milky Way is operating on a scale where our timeline becomes microscopic. And that's the emotional shift. The galaxy's scale doesn't diminish us, it contextualizes us. It shows us that we are not the measure of reality. We are participants inside something far older and larger, something that continues turning whether we watch it or not. So what does this chapter truly give us? It gives us a new ruler, not a distance ruler, a time ruler. A galactic year is about 225 to 250 million Earth years. Our Sun has completed about 20 to 25 orbits around the Milky Way since the solar system formed. Even at a speed of roughly about 220 kilometers per second, the orbit is still unimaginably long because the galaxy is unimaginably large. And this is the strange emotional payoff. Motion doesn't make the Milky Way feel smaller. Motion makes the Milky Way feel more real because it proves the galaxy is not a static picture. It is a dynamic system, a rotating architecture where time is built into structure, a place where gravity conducts a slow symphony that no human ear can hear in full, yet we can still understand the score. But we're about to face another uncomfortable question, because once we understand our galaxy's scale in time, we naturally want to know what kind of galaxy this really is, not just in isolation, but in context. We've measured our home by distance, then by thickness, then by invisible mass, and now by time itself. But this raises another question that refuses to stay quiet. If the Milky Way is this vast, this structured, this slow-turning, is it ordinary? Or are we living inside something extreme? Because the universe is filled with galaxies, tiny dwarfs, giant ellipticals, spirals larger than ours. And the only way to understand the true scale of the Milky Way is to set it beside other galaxies and see what it becomes in comparison. That's where the next chapter begins. We like labels: small, large, massive, average, because labels feel like control. But out here, on the scale of galaxies, those words collapse, because the Milky Way isn't just a galaxy. It's our ruler, our reference point, the only home we've ever known. So when we ask, how big is the Milky Way, we're really asking something sharper. Compared to what? Compared to the smallest galaxies, barely holding themselves together. Compared to giant spirals that feel like larger versions of our own. Compared to elliptical monsters, where edge stops meaning anything at all. And this is where the story cracks open. Because the Milky Way is enormous, but it's not the largest thing in its class. And that fact should disturb us a little, because it means our home is big enough to overwhelm the mind. And still, it's only one shape among countless others. When we imagine a galaxy, we picture one shape, a neat spiral, a glowing disk, a center. But galaxies are not standardized objects. NASA describes the range bluntly. Some galaxies are so small they span only a few hundred light years. Others can be more than 1 million light years across. That's not a difference in detail, that's a difference in category. So when we place the Milky Way on this spectrum, we have to stop thinking like tourists. We have to think like cosmic cartographers. Our galaxy, our home spiral, is commonly described as about 100,000 light years in diameter. That number alone is enough to break intuition, but comparison is what turns a number into meaning. So let's do what astronomers always do. We put our home on the table, and we slide other galaxies beside it. We begin at the bottom of the scale, dwarf galaxies. The name sounds gentle, but the reality is harsher. Some dwarfs contain only a few thousand stars. Some span only a few hundred light years. That's not a smaller Milky Way. That's something closer to a cosmic ember, a faint concentration of matter trying not to unravel. And many of them don't survive intact. They orbit larger galaxies like ours, and over time, tidal forces stretch them, strip them, absorb them. ESA describes dwarf galaxies as small systems with far fewer stars than giants like the Milky Way and Andromeda, and many are found as satellites orbiting bigger hosts. So here's the unsettling thought. When we compare the Milky Way to dwarfs, we're not just comparing sizes, we're comparing fates. Dwarfs are often the building blocks, and sometimes the victims of larger galaxies, and this creates a bigger problem. Because if the universe can make galaxies so small they almost don't count, what else can it make? Picture this. A dwarf galaxy is like a single neighborhood at night, a handful of porch lights, scattered, fragile. The Milky Way is like an entire city seen from high above, districts, highways, bright centers, dim outskirts, motion everywhere. Both are lights in the dark, but one can be swallowed by the other. And that's the quiet truth of scale. The Milky Way isn't just larger than dwarfs. It belongs to a different level of gravitational reality. Now, we climb. We leave the dwarfs behind, and we enter a more familiar architecture. Spiral galaxies, disks, arms, a rotating system that feels almost designed. And here, the Milky Way finally finds siblings. The most famous is Andromeda, Messier 31, our nearest major neighbor. NASA's visualization of Andromeda, built from swift observations, describes it as more than 220,000 light-years across, about 2.5 million light-years away. That number is a shock. If the Milky Way is around 100,000 light-years across, then Andromeda can feel like a larger echo, a spiral that carries the same idea, but scaled up. And suddenly we see something important. The Milky Way is not the default. It's one example, a large one, but not the ceiling. And then it gets stranger, because Andromeda isn't the only way to be bigger. Some spirals are stretched, some are richer in star formation, some are warped by mergers, some are calmer, some are violent. The spiral category isn't one object repeated, it's a family, shaped by time, collisions, and environment. So the Milky Way's size tells us something, but it doesn't crown us. It places us. Imagine this, as simply as possible. You're standing in your backyard at night. Down the street, far beyond what you can walk, there's another city, so distant you'll never reach it, but close enough that, on the cosmic map, it's basically next door. That's Andromeda. Not a star, not a blur, a whole galaxy, near enough to be our major comparison point. And if Andromeda can be more than 220,000 light-years across, then our instinct to call the Milky Way huge has to evolve. Because huge is not a finish line, it's just a location on a spectrum. Now we step into a different shape entirely. Elliptical galaxies. No arms, no neat disk. Instead, an immense, rounded glow. A galaxy that looks less like a pinwheel and more like a storm of ancient stars locked into a single gravitational body. NASA's Hubble material on Messier 87 calls it an enormous elliptical galaxy, home to several trillion stars, with around 15,000 globular clusters. Several trillion. We have to sit with that. Because when we talk about the Milky Way, hundreds of billions of stars by many estimates, we are already in numbers that the mind can't feel. But trillions is a different kind of weight, and ellipticals don't just scale up star counts. They often dominate their environments, especially in galaxy clusters, where gravity gathers matter like a slow, unstoppable tide. NASA's broader overview reminds us again, the largest galaxies can contain trillions of stars and can be more than 1 million light-years across. So here is the uncomfortable truth. Even if the Milky Way feels unimaginably vast, there are galaxies that treat our scale like a smaller chapter. And that's not the whole story, because size isn't the only measure of bigger. A galaxy can be wide and still relatively light. A galaxy can be compact and unbelievably massive. A galaxy can be bright and still be a minority of its own matter, with most of its mass hidden in dark matter. So when we compare the Milky Way, we're not just comparing diameter. We're comparing structure, history, and gravity's footprint. Spirals like ours tend to be organized, rotation holding the disk in a coherent shape. Ellipticals often look smoother because their stars move in more randomized orbits, a sign, in many cases, of a violent past. Mergers, collisions, reshaping. Dwarfs can be irregular, disrupted, or barely assembled. So what does that make the Milky Way? Not small, not supreme. A large spiral galaxy, significant, structured, and common enough to be a major category. NASA describes the Milky Way as a spiral galaxy, like a pinwheel, about 100,000 light-years in diameter. When we line that up beside dwarfs that can span only hundreds of light-years, and giants that can exceed 1,000,000 light-years, the conclusion becomes strangely calming. We are not living in the smallest kind of galaxy, and we are not living in the most extreme kind. We are living in a galaxy that is large, but not an outlier. So here's what comparison gives us, plainly. Against dwarf galaxies, the Milky Way is a giant, an environment that can capture, strip, and absorb smaller systems over time. Against large spirals, the Milky Way holds its own, but it is not the biggest spiral story in our neighborhood. Andromeda can be far larger in extent. Against giant ellipticals, the Milky Way is not the end of the scale. Ellipticals like M87 sit in another tier, trillions of stars dominating clusters, living like gravitational capitals. And that placement matters, because it reshapes the emotional meaning of our home. The Milky Way is not everything, but it is not nothing. It is one major expression of what the universe builds when gravity has time, and when matter is allowed to organize instead of scatter, and there's a quiet dignity in that. But this raises another question. If galaxies vary this wildly, and if size itself depends on how we define an edge, then how confident are we in any of these numbers? How do we measure the faint outskirts, the halos, the hidden structures that don't glow the way we want them to? Because comparison only works if the measurements are real, and that's where the next chapter begins. What our technology can measure, and what it still cannot. We keep asking a simple question. How big is the Milky Way? And the universe answers with a kind of cruelty. We don't get to stand outside our home and take a clean picture. We are inside the thing we're trying to measure. It's like trying to measure the size of a forest, while you're trapped deep between the trunks, surrounded by bark, fog, and distance. We can look up and see a ribbon of light, but that ribbon is not a diagram. It's a clue, and the most unsettling part is this. The more powerful our instruments become, the more clearly we see what we still cannot. When we say technology, we imagine a sharper camera. But in astronomy, a sharper camera is not enough. Because the Milky Way isn't hidden by darkness. It's hidden by material. Dust, gas, crowded fields of stars stacked behind more stars. So we don't just need better eyes. We need entirely different senses. That's why modern galactic measurement isn't one instrument, it's an alliance. Radio telescopes that listen through dust, infrared surveys that see heat where visible light dies, space astrometry missions that measure tiny shifts in position, star by star, year by year. And yet, every method comes with a cost, because every method has an edge where certainty collapses into probability. That's where the real story begins. Visible light is honest. It shows us what's shining, but the Milky Way is full of regions where starlight never reaches us. Not because the stars aren't there, but because something is in the way. Interstellar dust is not dramatic. It's not a wall you can touch. It's more like smoke in a sunlit room. So thin you dismiss it until the light behind it turns into a smear. And this is why the galaxy's most crowded places can be the hardest to study from Earth. We have to look through thick lanes of light-blocking material. So astronomers change the question, not what do we see, but what can pass through. Picture this. You're standing in the middle of a huge city at night in heavy fog. Streetlights glow, but the fog eats the distance. You can't see the edge of the city. You can't even see the biggest buildings. Now imagine you put on special goggles. With one setting, you can see warmth, the heat of people, engines, rooftops. With another setting, you can hear low sounds that travel through the fog. That's infrared and radio, not better vision, different truth. And with those senses, we begin to recover the shape of the place we're trapped inside. Infrared light can slip through dust better than visible light. That's why space-based infrared missions matter so much for mapping the Milky Way, especially the dense, dusty plain where so much of the galaxy's structure is hidden from ordinary sight. NASA's WISE mission, for example, surveyed the sky in infrared and revealed the Milky Way as an enormous band of stars and dust structures that don't show up the same way in visible light, and newer plans push deeper into the worst obscured regions. NASA's Nancy Grace Roman Space Telescope will use infrared vision and a wide field of view to peer through thick dust in the galactic plane, specifically because that territory is so difficult to study from our position inside the disk. But here's the strange part. Even with infrared, we still don't get a clean border. We don't see a crisp edge of the Milky Way like a coastline. We see gradients, star density thinning, dust lanes fading, structures dissolving into background. Infrared doesn't end the uncertainty. It just moves the horizon farther out. And that creates a bigger problem, because to measure scale, we need distance, not just detection. This is where the story becomes almost unsettlingly precise. To know the galaxy's size, we must know where stars actually are. Not over there, but how far over there. So astronomers use one of the oldest tricks in human perception, parallax. If you hold up a thumb and switch which eye is open, your thumb seems to shift against the background. That shift is distance made visible. Astronomers do the same thing, using Earth's motion around the Sun as the baseline and measuring a star's tiny apparent shift against much more distant background stars. It sounds simple, but the shift is so small that it becomes a test of civilization-level precision. This is why space astrometry changed everything. The European Space Agency's Gaia mission wasn't designed to take pretty pictures. It was designed to measure positions and motions with obsessive accuracy. Gaia built a vast, precise three-dimensional map of our galaxy by surveying nearly 2 billion objects and monitoring them repeatedly over time to chart their positions, distances, and movements. This is not just a catalogue. It's a living model of the Milky Way's skeleton, built from the measured drift of starlight across years. And once we have distances and motions, we can do something more powerful than imaging. We can infer structure, spiral arms, streams, the warp of the disk, stellar neighborhoods moving together like currents. But even Gaia has boundaries, because parallax is unforgiving. The farther the star, the smaller the shift. Eventually, the measurement becomes so tiny that uncertainties rise, and the galaxy begins to blur again at the edges. Not because we're ignorant, because we're reaching the physical limits of the method, and scientists hate mysteries like this, the kind that don't yield to effort, only to new tools. So astronomy turns to a different messenger. Radio waves don't behave like visible light. They can pass through dust in the galactic plane and carry information from regions our eyes can't access. And one radio signal is especially powerful for mapping the Milky Way: the emission from neutral hydrogen, the most abundant element in the galaxy. Hydrogen fills the space between stars, thin, cold, widespread. It doesn't announce itself with bright visible glow, but in radio, it speaks. That hydrogen signal can be used to trace gas across the Milky Way, and, when paired with motion measurements, help map large-scale structure and galactic rotation. Radio telescopes like the Green Bank telescope exist for exactly this kind of work, collecting faint radio whispers from hydrogen clouds and other cosmic structures. This is where measurement becomes cinematic in the most literal way. We map the galaxy by listening to what it cannot hide. But then comes the catch. Radio doesn't give us distances directly. It gives us velocities, how gas is moving toward or away from us. To turn that into a 3D map, astronomers must combine the signal with models of galactic rotation and geometry, which means the map becomes partly observed and partly inferred, and inference is powerful, but it always carries uncertainty in its shadow. With infrared, radio, and astrometry combined, we can map enormous portions of the Milky Way, but the edges remain difficult. Not because we lack intelligence, because the galaxy doesn't cooperate with clean definitions. The outer boundary isn't a wall, it's a thinning, a gradual fade in star density and gas, complicated by structures that extend beyond the bright disk. Distance uncertainty grows with range. Dust and crowding complicate surveys in the plane and toward the center. Radio mapping depends on rotation models and geometry, which can vary in detail. So the galaxy's scale becomes something we know, but never with the satisfying sharpness our instincts crave. This is why professional astronomy speaks in ranges, confidence intervals, and cross-checks. Not because they're unsure, because they're honest. Uncertainty does not mean ignorance. It means we understand what the measurements can and cannot support. And that honesty is the difference between science and myth. Here's what we've earned with this toolbox. We don't need a perfect photograph of the Milky Way to measure it. We need a network of constraints. Infrared surveys reveal stars and structures that dust tries to bury. Parallax and precise astrometry turn the sky into a measurable depth field, star by star. Radio observations trace hydrogen across the disk, including regions visible light can't penetrate. Each method alone is incomplete. Together, they form something stronger than a picture, a working, testable, continuously improving model of the galaxy we live inside. A map built from motion, heat, and faint signals. A map that admits its own limits and still holds. But this is where everything changes, because even when the data is solid, even when institutions like NASA and ESA build missions that turn the Milky Way into a measurable structure, something inside us still refuses to accept it. We can understand the scale, we can repeat the numbers, but we don't feel them. And that fracture between comprehension and intuition is the next frontier. Because the galaxy isn't only difficult to measure, it's difficult to imagine. And in the next stretch of our journey, we confront the strangest limitation of all, not our instruments, our minds. We can say it, we can repeat it like a prayer of numbers. A galaxy so wide that light takes 100,000 years to cross it. And yet, nothing changes in our chest. No vertigo, no real fear, no real awe, just a clean sentence. And that's the unsettling twist. Because the Milky Way is not hiding from our science anymore. It's hiding from our intuition. We can measure it, we can map it, we can prove it. But when we try to feel it, the scale slips through our minds like smoke through fingers. And that raises the real question of this chapter. Why does the truth still feel abstract, even when it's correct? We are not broken. We are simply built for a different world. Our brains evolved to track what mattered on the ground. Distances we could walk, threats we could outrun, faces we could recognize, seasons we could survive, meters, not light years, minutes, not millions of years. So when we attempt to hold galactic scale inside a human nervous system, we're asking an ancient tool to do a modern job. And the tool does what it was designed to do. It compresses reality into something usable. It turns the unimaginable into a symbol, a diagram, a label, a number we can speak, without having to carry the full weight of what it means. This isn't a flaw, it's a shield. Because if our brains processed cosmic scale the way they process a cliff edge, we wouldn't be able to sleep. 1. Our senses don't measure the world, they simplify it. Even in everyday life, our perception isn't a perfect ruler, it's an interpreter. Sound doesn't rise in our experience the way it rises in physics. Brightness doesn't scale in our feeling the way it scales in photons. Our senses compress big ranges so we can function, and that same compression happens with distance. A few meters feels different from a few kilometers. But beyond that, our intuition begins to flatten. 100 kilometers, 1,000. They stop being places we can feel and start becoming quantities we can only label. Now, imagine pushing that into the realm of light years. Our minds don't expand, they simplify harder. So when we hear 100,000 light years, the brain often does something quiet and automatic. It replaces the reality with a token, a word, a concept, not a lived space. And this creates a deeper mystery. If our minds compress scale by default, how can we ever truly understand the galaxy we live inside? 2. Diagrams save us and betray us. We rely on diagrams because we have to. A spiral drawn on paper feels manageable. The sun becomes a dot, the disk becomes a shape, and in one glance our brains finally get something they love, a whole object. But here's the strange part. That object is a lie of convenience. Not because the diagram is wrong, but because it has to break reality to fit inside our eyes. A galaxy can't be shown to scale on a screen while still showing our position inside it. So diagrams compress, they flatten, they cheat. And if we aren't careful, the brain believes the cheat emotionally. We start to feel like the Milky Way is something we could hold, something we could wrap our arms around. But we can't. We live inside it. We are not observing a spiral. We are embedded in a rotating, layered, dust-filled system that extends far beyond what the sky shows us. Diagrams give us comprehension, but they quietly steal the emotional truth. And this is where everything changes. We can be factually correct and still be emotionally misled. 3. Our minds understand near and now, not far and forever. There's a reason distant things feel abstract. A memory from last week feels detailed. A memory from 10 years ago feels like a story. A place across town feels real. A place across the world feels like a picture. The farther something is, across space or time, the more our minds turn it into an outline. And the Milky Way lives at the extreme end of that distance, not just in kilometers, in experience. We can't walk its width. We can't watch it change in a lifetime. Even our sun's orbit around the galaxy takes longer than the entire existence of human civilization by an unimaginable margin. So our minds do what they always do when faced with too large and too slow. They step back, they trade detail for abstraction, and suddenly the galaxy becomes a concept, a cosmic fact, something we know, but don't inhabit. And that's not the whole story. Because even though our intuition collapses, our science does not. Imagine this. You hold a printed map of your entire city, every street, every neighborhood, every landmark. Your home is there too. But it's not your home anymore. On the map, it's a tiny dot. You can point to it. You can explain where it is. But you can't smell the rain on the sidewalk. You can't hear the distant traffic. You can't feel the weight of the air before a storm. The map is true, but it is not the experience. That's what happens when we try to hold the Milky Way inside a diagram. We turn a living environment into a symbol we can carry. We don't do it because we're careless. We do it because it's the only way our minds can hold the scale at all. So we arrive at the central fracture. There are two different kinds of knowing. Understanding is when we can explain how astronomers use parallax, how ESA's Gaia maps star positions and motions, how radio surveys trace gas through dust, how gravity reveals mass we can't see. Understanding is the intellect. It's the part of us Einstein trusted when he followed equations into strange territory where intuition could not guide him. But feeling is something else. Feeling requires reference points, something our bodies recognize, something we've lived through. We can feel the height of a building because we've stood under one. We can feel the distance of a drive because we've watched the road pass beneath us. But we have no lived reference for a light year, no memory that anchors the idea. So feeling doesn't activate, the mind remains calm, the number remains clean, and the galaxy remains abstract. That's not failure. It's the price of being human. And yet, it hides a quiet triumph. Because even though we can't feel the Milky Way instinctively, we can still know it. You can imagine walking across your room. You can imagine walking across your city. You can even imagine circling Earth. But try this. Try to imagine traveling to the nearest star beyond the sun, not as a number, as a journey you can feel. Most minds do the same thing. They reach for an image, and then the image dissolves. The brain goes quiet. And in that quiet, it's easy to believe the scale is meaningless. But the silence doesn't mean the galaxy is unknowable. It means intuition has reached its boundary. Science begins where intuition ends. That's what missions like Gaia represent. That's what NASA and ESA represent. Not machines replacing us, but machines extending us beyond what our senses were built to handle. So here's the real payoff of this chapter. The Milky Way isn't too big to know. It's too big to feel. Our brains evolve for local survival, so they compress scale. Diagrams simplify what cannot fit inside a single image. Distance and time turn reality into abstraction. And yet, despite all of this, we have mapped our place. We have measured the galaxy not through instinct but through method, through repeated observation, through cross-checking, through humility about uncertainty, through the refusal to pretend we see what we don't. This is why uncertainty in astronomy doesn't mean ignorance. It means honesty about the edge of our tools, and that honesty is the foundation of everything we've learned. The Milky Way is vast, but it is measurable. Not because our minds are naturally suited to it, but because we built a way to know what we cannot intuit. And that leads us to the final transition. Because if the scale breaks the human mind, what does it do to the human story? Now we face the final door. If we accept that our intuition will never fully contain the Milky Way, then what remains? What does it mean to live inside a structure this large? To realize that every war, every song, every childhood, every hope has happened inside a tiny region of a galaxy that will outlast us beyond comprehension. This is not a question for instruments. It's a question for meaning. And in the final chapter, we don't chase a measurement. We sit with the answer. Because the Milky Way doesn't diminish us. It contextualizes us. And learning its scale, quietly, honestly, can become an act of humility without becoming an act of despair. We spend our lives under a sky that looks quiet, a soft band of light, a handful of bright stars, a darkness that feels empty. But that calm is a trick, because the Milky Way is not a picture we can step back from. It is the room we are standing inside. And that creates a problem that sounds almost childish until it becomes unbearable. How do we measure a home we can't leave? How do we measure a structure that surrounds us in every direction when our eyes only see a thin slice? We want a clean number, a simple border, a final diagram. But the galaxy doesn't give us that. It hides behind dust, it hides behind distance, it hides behind our own human scale. And yet, we still measured it. Not perfectly, not effortlessly, but accurately enough to say something that would have sounded impossible to every civilization that came before us. The Milky Way is vast, and we know where we are inside it, and that fact changes the meaning of home, because it means we are not trapped in mystery, we are living inside an answer. But this is where everything changes, because knowing the size of the Milky Way is not the same as feeling it. And the final chapter is not about adding one more number. It's about what those numbers do to us when we finally let them land. When we say we've measured the Milky Way, we don't mean we took a cosmic ruler and stretched it across the sky. We mean something more human. We mean we listened, we watched, we noticed patterns, and then we built a map from the patterns. This is the quiet power of science, not certainty in the arrogant sense, certainty in the patient sense. Astronomers didn't win against darkness by seeing more. They won by changing the question, not, what does the galaxy look like from outside? But, what must be true based on how everything moves inside? It's the same kind of thinking Einstein used when he taught us that gravity isn't a force you hold in your hands. It's a shape written into space itself. You can't always see the shape, but you can see what it does to motion, and motion never lies for long. Here is the uncomfortable truth. We have never photographed the Milky Way the way we photograph Andromeda. We can't. We are embedded inside the disk, surrounded by dust and gas that block our vision in many directions. So, the galaxy forces us into a strange position. We are like someone trying to map an entire city while standing in the middle of a foggy street with buildings towering above. We can see some lights nearby, but the skyline, the edges, the true shape, hidden. And this created a bigger problem. Because the Milky Way isn't just large, it is large on a scale that breaks human instincts. 1,000 kilometers feels far. 1,000,000 kilometers feels unreal. A light year isn't even a distance our bodies can respect. It's a time-laden unit, distance measured by the travel of light. And yet our galaxy is measured in tens of thousands of those. So how did we do it? We used 3 silent messengers: light, motion, gravity, and each one carried a different piece of the truth, but none of them delivered it cleanly. Because the galaxy doesn't have a sharp edge, it fades, it frays, it dissolves into a halo of sparsely distributed stars, gas, and unseen mass. So every measurement comes with tension. We know the scale, but the border refuses to be precise, and scientists hate mysteries, not because they fear them, because mysteries are unfinished maps. Let's place the facts on the table, slowly. The Milky Way is roughly 100,000 light-years across. Our solar system sits about 26,000 light-years from the galactic center, and the Sun takes about 250 million years to complete one orbit around that center, 1 galactic year. Those are not guesses scribbled in the margins. They're measurements built from decades of observation, radio astronomy, infrared surveys, and especially precise mapping missions that track where stars are, how they move, and how their light shifts. One of the most profound examples is ESA's Gaia mission, a spacecraft that has made more than 3 trillion observations of about 2 billion stars and other objects, constructing an extraordinarily detailed 3-dimensional map of our galaxy's contents and motions. 2 billion. It's hard to hold that number, so let's translate it into something we can picture. Imagine a massive stadium at night. Now imagine every seat is a tiny light, and then imagine the stadium is so large and so crowded that you can't see the far wall through the haze. Gaia's job is not to photograph the whole stadium from outside. It's to stand inside the haze and record the position and motion of billions of those lights, so we can reconstruct the shape of the stadium anyway. That's what makes this achievement so unsettling. We are not measuring the Milky Way the way we measure ordinary things. We are measuring it the way a blind person learns the size of a room, by the echoes, by the footsteps, by the pull of gravity, by how everything behaves in the dark. And somehow, it worked. This is the quiet miracle of our era. We can point to our location inside the Milky Way and say, without romance, without mythology, we are here, not at the center, not at the edge, in the disk, in a spiral arm region, orbiting along with hundreds of billions of other stars. And what comes with that is not insignificance, it's orientation. For most of human history, the Milky Way was a mystery painted across the sky. A river, a road, a scar, a divine seam in the heavens. Galileo turned a telescope toward it and shattered the illusion, revealing it was made of stars. Later, astronomers argued fiercely about what that meant, how large it was, whether it was the entire universe. Then the universe cracked open again, revealing other galaxies, and the Milky Way became what it truly is. Not everything, but an enormous structure that still contains everything we have ever been. Even now, even with all our instruments, every language, every war, every prayer, every song, every scientific paper, every heartbeat that ever happened on Earth has occurred inside a tiny region of this one galaxy. That's not a poetic metaphor, that's geography. Picture this. You're standing in your home at night, the lights are off, you can't see the walls clearly, but you know the house is there because sound behaves differently in each room. A hallway carries footsteps, a small room holds echoes, a large room swallows them. Now take that feeling of knowing a space by what it does, not what it looks like, and stretch it to the Milky Way. You have never seen the full shape, but you live inside the evidence, and that's what should feel disturbing. Not that the galaxy is big, but that we can know its scale, while still feeling how helplessly small our senses are. Our technology did not give us a perfect portrait. It gave us a framework, a scaffold of truth. NASA's summaries are blunt and almost understated. The Milky Way is about 100,000 light-years in diameter, with our solar system about 26,000 light-years from the center, and one orbit taking about 250 million years. Those statements sound calm, but their implications are catastrophic to intuition, because once we accept them, we have to accept what comes with them. We will never travel across the Milky Way in any human sense. The galaxy is not a destination, it's a time scale. Our entire species has existed for a fraction of a single galactic orbit, and yet we measured it anyway, using methods that don't demand heroic journeys, only patience, only precision, only the willingness to let the universe speak in the language it prefers. Numbers, motion, light. There is a common emotional trap here. When people hear 100,000 light-years, they feel erased, as if size equals value, as if vastness is an insult. But that's not what scale means. Scale is context. A mountain doesn't diminish a person. It reveals where a person is standing. The Milky Way doesn't diminish us. It locates us, and that changes the emotional temperature of existence. Because we are not floating in an undefined void. We are part of a structured system, an ancient rotating city of stars whose dimensions we have learned to trace. And that knowledge is not cold. It is intimate. It means the universe is not completely beyond comprehension. It means our minds, small as they are, can still reach outward and touch the architecture of reality. Stephen Hawking once warned that the universe doesn't owe us comfort, but the universe sometimes offers something else. Clarity, not the warmth of certainty, but the steadiness of understanding. So this is where we end, not with a final image, but with a final orientation. The Milky Way is vast, but measurable. Its size is known through motion, light, and gravity. We are not lost inside it. We have mapped our place. But the universe had one more twist, because the moment we stop feeling lost in the Milky Way, we start asking a deeper question. If we can measure the scale of our home while trapped inside it, what else are we living inside, right now, without realizing it? A larger structure, a wider pattern, a cosmic neighborhood, with edges we haven't learned to name yet. And that is the quiet invitation. Tonight, or tomorrow, whenever the sky is clear, look up, not for comfort, not for escape. Look up to remember that we are inside something vast, and we are capable of knowing it, and in that knowledge, there is a quiet kind of peace, not because the universe is small, because we finally stopped asking it to be.